Good morning, everyone. Welcome back from the break. I'm Jacob Zach, a member of the DNS-OARC Program Committee. I'd first like to welcome to present David Dagon. He's a research scientist from Georgia Tech, and he's going to give a presentation on local DNS policy disclosure.
Thank you. As the program committee earlier noted, I'm a replacement speaker. So don't expect to actually get to have a talk. These are a collection of notes that were gathered over the last day or so that I thought would result in a very thoughtful email to a mailing list. But when the organizers asked if I had anything prepared, this is what was ready. So I'd like to start with a bit of a story, sort of an amusing anecdote about the topic of DNS filtering. There was a time in the United States when federal legislation was being debated and considered to mandate filtering technologies in US ISPs. And this was largely around copyright protections, although that would have been the opening of the door to all sorts of other filtrations. And at the time, I worked with a group of folks, Vixie and Steve Crocker, Danny McPherson, and Dan Kaminsky. We wrote a little white paper early on saying, this is architecturally a bad idea. Here are all of the reasons why federally mandated filtering would be problematic. And this white paper was one of the many reasons that people started to pay attention to the issue. And oddly, at one point on Google's homepage, this, you can't see it in there, but my name appeared on the front, which does extremely odd things to your inbox. When Google.com essentially has a link back to documents you've written. But this ended up opening a lot of doors, and people wanted to meet with us and figure out what were our objections really about. And we ended up taking a series of trips to Washington, D.C. and meeting with members of Congress. There were dozens and dozens of meetings, and I came away with a new, both a healthy respect and a disgust of lobbying. It's utterly impressive and wrong at the same time. But the density of meetings had one notable example. We were ushered into a room and told that I'll just call them a famous congressman would be with us shortly. His staff was there, and we were chatting. And in walked the congressman, who normally I see on television. It was, one of those gee whiz moments. And he turned to his staff and said, "Are these the guys?" Which seemed like a good sign. And then he reached over and grabbed out of Dan Kaminsky's hand a copy of our white paper. And he said, "I'm going to tell you how to fix this report." And at that moment, everything I'd ever been taught as a child about democracy and how legislation works was validated. It seemed to me that, wow, here's a policy insider. He's going to offer some very good suggestions about how to adjust this white paper so it reaches a better audience. Democracy works. This is, I can't believe this moment. And then the next words out of his mouth were, "This needs to be twice as long. You can double space it. Don't print it on both sides. Increase the font, bump it up, get me 20 pages I can wave around in a committee." And then we went to the next meeting. Each of these meetings were no more than 5 to 10 minutes, and I will say at some of the meetings we actually had members of Congress sitting down, and we would pull out pieces of paper and walk them through DNSSEC validation step by step with very detailed follow-up questions that expressed interest in learning, as well as a probing need to understand if our objections were based on sound reasoning and science. So it was at both ends of the spectrum, and the distance of time have let me appreciate that actually sort of both approaches have some validity. It's often the case that when we're faced with a question of policy, we hold up a stack of papers or hold up a community or hold up a principle and wave it about and tell others, you need to respect this. It's simply the packaging and the detail and the thoughtfulness that goes into that really matters. And so our community is sort of faced on a regular basis with various changes of the protocol, and these in turn raise resolution policy questions similar to SOPA PIPA. They're obviously intended to go in a different direction, but they bring to the fore the question of who has relevant information, what rights and interests need to be respected, who are the bad players, what is the problem we're trying to address with this policy and protocol, and have we fully understood the dimensions of the problem. And so with the most recent discussion around DOE, we've, in some cases, I think, been pointing to this question of DNS filtration and pointing out, rightly so, that in many cases it's a villain. It's being done for oppressive purposes. And the last few days I've been pointing out to people there's actually a lot of industries and operators that do DNS filtration for perfectly legitimate reasons to protect their users. And I wanted to try and offer some language around why some of those operators are good, some are perhaps in need of improvement, and some, as some of the protocols and discussions have identified, are problematic and need to be addressed. And so I thought we'd review a few of them. In some of the discussions with peers here, it became obvious to me that they haven't necessarily been exposed to DNS filtration, which seems unusual for DNS operators, but I guess is likely. There's a lot, and really this will end up becoming a survey, a paper of some sort, but here's a few just to start with to give you a sense of some of the major flavors that are out there. This is a page from a researcher at a university in France, and for a decade or so, he has published one of the most beautiful hand-curated lists of domains with dozens of categories, everything from adult content, aggressive websites, hacking, advertising, sports, every possible category you can think of. And it's offered under a Creative Commons license. Even before Creative Commons was available as a license, it was a blacklist collection that was out there, available freely. And his caution is that you shouldn't be blocking these. You should be discussing within your organization whether these categories are useful, and it might help you understand the information that you're seeing in your logs. And actually, if any of you use antivirus products at all, you should thank this person, because most of the AV industry takes this. It's free. I hope that he's in some way been rewarded or thanked. It is Creative Commons, so there's perhaps no need, but I think some praise is worthy. But most AV products out there have this, plus a lot of their own secret sauce. They at least have these blacklists. And there's a lot of other blacklists like this. There's dozens of carefully hand-curated lists that individuals have made. And their intent is not to vilify certain collections of websites, but to provide categories so that administrators faced with certain mandates like do not allow adult content in the classroom for children, do not allow time-wasteful domains to be used in a facility concerned with security. These sorts of things are most easily done if you have lists, and there's lots of lists that are out there. There's also corporations, many of them, and I just picked one at random because as I started to revisit all of my bookmarks of these DNS filtration companies, I noticed that many of them had updated their offerings to say, you have to do TLS inspection now. It's no longer that they have a nice blacklist, probably just a nice collection of all the open source ones, but now they're also noting that their deployment for their MSP solution will now have some sort of TLS interception involved. And there's a much more thorough, thoughtful talk, not one put together in a few hours at a conference to fill in a vacant slot, would of course drill down into what that means and the types of TLS inspection, and is it in response to DOE, and what are their thoughts in that area. There's also another major family, and if you're under 30 years of age, this makes sense, but their installation model generally hinges around pulling something from a website, sometimes not even HTTPS, and piping it to bash. It makes sense for kids today, and those of us who've lived through this type of era before see this as a form of self-immolation. Nonetheless, it's a very successful model and a very fine home-directed security product. You can block different categories of unwanted things, mostly around ad networking seems to be the major focus. It saves on bandwidth costs, keeps you under your metered bandwidth cap if your phone is limited in some respects. But there's a whole variety of these, and my intent is that when I have more than just a few hours to put some notes together on a slide, I will complete a survey of these and note the different architectures that they're using and whether or not they are responsive to the protocol developments that this community is discussing. Pi-hole actually here is, and is paying attention to DOE and will be updating their code to reflect the existence of this protocol and provide users choices. So I don't have this survey. I have noted that other people have this or have something like it or are in that work area, and I'll be reaching out to them. I do note, DNSprivacy.org is an excellent starting point if you want to get more than just the few offerings I've provided. I think no matter what you look at, you're going to find that the underlying most important concept is informed user consent. If you're doing filtration, if you're stopping people from looking things up, mandatorily, you have to tell people this and get their permission to do it. Now, there's a whole spectrum of what that really means. Sometimes it means you clicked OK, there was 80 other clauses and paragraphs that you didn't read. One of them involved filtration. Sometimes it's merely implicit in network access, and sometimes some network operators point to DHCP as their notice and consent. You got on my network, you play by my rules, or the switch drops you. I think if we're going to be in this era where we want to address through protocol problems of filtration to enable people to reach sites even though some people are trying to stop them, I think a very important differentiator is this notion of informed consent. And towards that end, we need a way for users to discover what the policies are in network. Now, this is not really a new concept. If you look at the old, some of the older regulations, 2002, the e-privacy directive, the cookie dropping law in Europe was really about informed user consent. The more recent updates of GDPR are about not merely getting permission to write to a user's local file instance, but to also give them control of that data with various other dimensions of rights. And although the U.S. clearly lags behind in the regulatory space here, there are a lot of policies and developments in the private space that embrace this notion of informed user consent. And so I think it's a universal principle. And so as we talk about this question of DOE and filtration and what is or isn't legitimate, I think this is probably a good guiding star for that discussion. So with that in mind, I was just the other day, thinking about this and talking to some friends at the conference saying, what if we had a website that if you looked it up, you tried to resolve it, and there were a local DNS filtration system, it would know that that's a special website, there's no content there, and it should try and perturb the answer, either allow the answer to go through when it shouldn't or block the answer as a sort of binary indicator to the browser so that on startup, browsers could, and other applications could check, is there the possibility of reaching or not reaching a particular site, which I know is a special policy domain. Well, some logical places to put that would be under example.com or ICANN. Probably the right place is under .arpa. And many of you at this point are saying, Dave, don't you read your email? There's a proposal that just came out a week ago. Yes, I'm getting to that. I hadn't read my email at that point. It's only came out a couple weeks ago. And so my ideas here were slightly different, and I think they might contrast the idea. So one is that you could have DNS-policy.ARPA. There might be subdomains like refused, NX domain, and it might be that an A record returned in resolving this would be a local site at which other textual information could be placed so that the system administrator could post information on an internal website, reachable through the resolution of this domain. The idea is that this is found only in iteration, or in recursion locally, not in iteration. It's not globally reachable in some way. And then perhaps these dialogues we're presenting to users might have some more information besides, here's your existing DNS, do you want to keep it or not? There might be a reason why, because it's being at least somewhat honest about filtration. We've done this before. If you look, for example, at all of these other spaces, there are fake or globally reachable domains that really have a secondary meaning. Chrome, for example, famously on startup, does, let me skip to this here, does a randomized lookup of 3 non-existent domains to check whether there is a rewriting on the LAN. And sometimes this is confused by network administrators as malicious behavior. Sometimes malware tries to make itself look like Chrome in this startup phase. And in a lot of other contexts, we've found that there are special policy type domains. For example, Microsoft has an entire company internally that's fake. It's Contoso. And if you're trying to learn how to configure all of the various tools and products they have, you'll work on the Contoso Corporation without the fear of leaking your testing onto the global internet. Of course, your internal testing of it does leak if you use the domain Contoso. So all the domain controllers here are reachable because of the Windows resolvers leaking at least one internal name. DOE will make potentially all of the split horizon information available. But every time you see a Contoso lookup, you know that a MSSP is getting its wings. So we've had these special use domains in a lot of other contexts. I think it might be useful if we could tell the browsers explicitly. For example, Chrome on startup might preferentially start with checking out DNS-policy.ARPA or some random child label thereunder. And if there is a DNS editor, a filtration device that changes the answer, immediately Chrome knows, oh, I have a policy context here. They actually are changing answers. They're doing some sort of filtration. And that may be sufficient for them to not do other checks. Obviously, the browsers would not believe denials that there's any filtration there, since that's too easily gamed. But one possibility would be that it might cut down on the NTLD pollution aspect of that behavior. So all these random lookups are winding up in various logs and then restricting what can be registered as sunrise periods for new TLDs. We've typically addressed this by saying the passive-aggressive phrase, contact your local administrator. And I think it's time that we provided some concrete way of doing that. As it turns out, there is such a proposal. It just came out, and my approach is slightly different. Theirs is, actually I think all of the authors are here, so I'll just briefly summarize and they can correct. But the idea is that there would be a IJSON response to a new RR type, resinfo, and that there would also be a well-known domain, so you could reach this over HTTPS or DNS. It's intended to be internally used, and it would be a way to communicate structured JSON responses to a stub so that they can understand dimensions of policy, and there would be various fields. And my entire idea, which was around just a binary check, really fits as one special use case under that, so maybe theirs is a superset. Here's a comparison, really, of the two sort of side by side. My idea was to keep it simple and just have an A record because that works. In terms of a policy format, the answer you get back is the Wild West. There would be a web page that maybe the browsers want to check or show or not. I left it open. Some people have suggested YAML or some structured text. We're marching towards the IJSON solution that the draft had identified. The adoption, I think, of just an A record is trivial because you can tell people that you can just put it in right now, it'll work. I would worry about the following problems. There's a multipath problem where users have multiple DNS paths. One of them is filtered, one of them isn't. And if we have a global zone that consistently refuses to be answered, that would allow trivially some of these tools to start up and test other DNS resolution paths. So you could fall back to your secondaries in Windows and your less preferred DNS resolution paths trivially by knowing through a lookup you will get it refused. The DNS amplification problem is something that I think would be worth discussing on list. A simple A record seems small and lightweight. It doesn't contribute to the size of the ocean. If you're handing out JSON objects, those get large. If those objects that are large are not keys, there is a legitimate cost-benefit discussion that comes about. Obviously, policy has a benefit, but maybe it's a pointer to the policy that's handed out, and it's much smaller. So there's some equities that need to be considered there. And then the final would be around the scope. So you've got whether switch operators seeing these packets clear their routers should treat them as leaks because they were intended to be something only between the stub and its local recursive. What happens when somebody sends these queries across the larger internet to learn policy? And so there's a whole series of what-ifs that might be discussed. This was just drafted, and perhaps the scenario that I vetted with a number of people may fit as a special case in there. I will say there's a lot of other dimensions that time doesn't permit to cover, but I think one of the most important is that we do not provide to one side or the other a greater advantage vis-a-vis the censorship state versus a dissident who's trying to reach information. Same thing with the ad blocking software. There's a bit of a policy war going on in browsers where there are plugins that block ads, and there are advertisers who don't want that to happen. I don't think any of those solutions arm one side or the other with a new tool that gives them an advantage. Each of those beliefs need to be tested with certainty, and at least when it comes to the dissidents, I think reaching out to the Munk Center and other industry experts is the minimum, because accepting someone's assertion on a mailing list that this can't happen has not always to be borne out. So there's a lot more to discuss there, but I think that the guiding star that I'm convinced of now is that informed user consent is something that we need to expose. And if all of these edge devices, the browsers, the administrators had this information trivially reached through a well-known protocol or well-known port, that this information might become more available to users, and that, if you look at all of the policy guidelines that have actually worked over the years, is the guiding star and the goal. So no doubt there's going to be a lot of objections and what-ifs, but I await your comments.
Okay.
So we have, I think, one coming to the mic here. But
Hazel Smith, this is slightly tangential, and maybe I'll get shot for it, but read the comment that sending back a large JSON blob has a potential problem for DNS amplification usage or something. What if you insisted in the standard that implementation should always send back a truncated response and require it to be requeried over TCP?
right. So another way to avoid the spoofed amplification part is to insist that at least this little type of query should be TCP only. But I worry that there may be a downtrodden group of stubs that don't have TCP that rely upon TCP from the resolver. There may be forwarders that are not as sophisticated. So that is a solution.
Or make it CNAME to a nonce that then has the actual policy. So you got to get the CNAME back, then query for that. Yeah. So seems like one family of solutions is to use existing query types, A records, text records maybe, and CNAMEs, things of that sort, and just point to something that a browser or a user would know to load. That's one solution. It's small, lightweight. But the problem is that then at the global scale,
when you see these types of queries for, whatever, policy.arpa, you don't know if that's a leak or just a misconfigured Perl script that's trying to crawl the internet and look things up. So it's much easier to diagnose if there is a given, a new type to filter for, because then you know it's intentionally asking about policy or presumably so.
Yeah,
so,
you just have to hope your stub actually knows how to request and,
Yeah, so I would, particularly if the records are large and it's not a DNS-SEC key, which has an obvious benefit, a very large benefit, I think we do need to engage this question of cost-benefit analysis. Could we have made it smaller with a pointer, perhaps, and let the loading happen over 443, right, or port 80, or whatever local HTTP path they're using?
Thanks.
Brian Dixon, GoDaddy, just free associating on some of the potential things. I'm kind of loath to even suggest this, but there are things that are in not great protocol things right now, like SPF, where you can reference somebody else's. That might scale better for things basically saying include the policy of this and the policy of that because I'm using this service and that service. Or there's some pre-existing text that can be used from some other place. So like the actual thing that would actually be published for the vast majority of cases would be relatively small pointers to other things. Just a thought.
Right. So I would encourage you to look at the draft that I had neglected to read until last night before I talked to a few folks. And it appears that it would be possible to structure the JSON response so that you get simply an inventory as the minimum response, and then users would have to solicit individual fields one by one to build a full list of what records are there. That's one approach. There are other analogies, and there probably are some lessons that should have been learned from looking at what happened with SPF.
Yeah. Joe Abley, PIR. I feel like I've not understood your suggestion, your proposal a bit. Are you suggesting that an end device could discover that some local policy exists, give the user the option to decide whether or not that's something they believe in, so they can decide whether they want to circumvent it or not?
So the idea would be that there's a global zone that, let's say, shouldn't resolve or always does resolve, and then any DNS filtration device that wants to be discovered, that wants to be honest and be part of the discussion, would then see that query and take the opportunity to really suppress. There would be no iteration. There would be no need for that. It would perform filtration internally and provide either pointers or strings or JSON or indication back to the device. You are actually in the presence of a filtration device, because were I not here, you would have seen an answer that you know from the RFCs or however this is codified as either a failure or some sort of cached answer. So that's the idea, that it's a proof point for the existence, a proof of work that there is a filtration device.
So a well-behaving filtration operator could announce that they are there and give the user an opportunity to know, and that's where the consent comes from. Is that the
Well,
point of it?
Here's a good example.
I'm struggling to see how your case of a malicious filterer who's trying to filter users without their consent.
This doesn't
Presumably could just publish a policy that's something really benign, and I'm trying to optimize your kitten delivery or something, and people to induce someone to say yes. I'm not convinced I understand which problem of the original page this solves.
It is my assertion that the vast majority of filtration are good people trying to do the right thing, and they want to be transparent to their users, and if given a path to tell the users that they exist and what they're filtering and why, they would. There are, of course, people who will never disclose that, who are doing it for malicious reasons, and there are DOE will address that problem squarely, right? So the idea is to allow the people who would be truncated under DOE, who would be prevented from doing benign filtering under DOE, from even being part of the discussion, because the browsers, when they start, wouldn't know, is this a good person or bad? Are they trying to provide informed consent to the user or not? And so this is a small proof point. I don't believe it upsets the metric. If one person lies that they are a malicious filterer and they claim to be good and transparent, I don't necessarily know that it gives them any more power than they already have, right? So it doesn't arm them to, suppress user content any better that I can think of. It's worthy of debate, though.
So Warren Kamari, Google, and kind of following on from what Joe said, and somewhat answering it. In some ways, this feels very similar to the captive portals where employers, pop up the page or whoever saying, you don't have to pay us any money, you don't have to do anything, but you have to provide the user's consent that they're getting on the network and acknowledge stuff. And related to that, it feels as though some of this could actually be tied into the captive portal working group type stuff. A way to say, this is where the captive portal type page is, which asks for whatever, and maybe sort of some additional annotation specifically listing what DNS filtering or not the network provided as.
Yeah, exactly so. And if you think about it, a arbitrary JSON field also allows for a refresh of chaos text records. So we could revisit that and provide internal information that might be truthful as opposed to false information to the wider internet if they're answering chaos. Right, so there's a lot of other areas besides just this one problem of DOE. And I think the draft contemplates that. So my to-do list includes talking to the captive portal community.
Vittorio Bertola, Open Exchange. Thank you, because I think that this is the discussion that is necessary now, in the sense that DNS filtering has until now been a hack, which was not officially part of the DNS architecture. And I think we are at a point in time in which it needs to be a part of the DNS architecture, because this would bring some kind of transparency, at least for users and for everyone. And I just wanted to suggest that there are a couple more dimensions that should be considered when you want to describe, in whatever way, what kind of filtration activities is happening. One is that I would expect a lot of this filtration to depend on who you are and where you come from. And even in regulatory terms, I see it happening that, at least in Europe, we could get something like the GDPR, in which even if a resolver is not in Europe, it's expected to treat you differently because you're European and apply certain policies that they would not necessarily apply to other people. And also another dimension is that not everything happens with user's consent. And again, there's a discussion on values here, which is also part of the problem, in that in certain parts of the world, the freedom of expression is the #1 value, and so everything which is limiting that, even for other good reasons, comes as a second priority. In other parts of the world, other things are considered more important than freedom of expression, even in constitutional terms. So there are parts of the world, and I'm not referring necessarily to authoritarian countries, even in democratic countries, like in Europe, there are places in which it's considered more important in general for some content not to be accessible, even if you're limiting someone's freedom of expression to express it. And in that case, there might be some filtering that happens without the user consent. So in that case, it's good that it's transparent. So at least adding a dimension of transparency is useful. But there should be a way maybe to signal that this is being done even without the user's consent. And then if the user wants to employ DOH or whatever to bypass it, then it's the user's choice and it's fine.
Yeah.
But, yeah.
The earlier parts of my slides I was trying to get to this, that your exact comment, which I think summarized it better, that there is a universality to this idea of informed consent. We all have different policies and rules in different organizations, but there is at least this notion of giving users notice and making them informed, and then only taking action when they have consented. That's across all jurisdictions that I've seen. The only people who don't want that to occur, we tend to look at, we have different names for them. We call them malware authors, or we call them dishonest in some way. There are legal treatments for that type of behavior where you mislead people or take away their consent. And so I think providing a standardized mechanism for exposing that just in the stub, just in a local LAN environment would be very useful, even if every other jurisdiction would have a completely different response. So with no more comments, I'll remind you again that this was a replacement talk, not a real talk. And if you do have strong reactions, you're going to the reviews right now, perhaps go to the mailing list, not for my benefit, but for the benefit of the authors who did a far better job anticipating this issue and getting a draft together. So, thanks.
Thank you very much, David.
We would like to invite to the podium Geoff Huston from APNIC Labs, who will be presenting what part of no is so hard for the DNS to understand.
Morning all. This is a lightning talk under any other guys because I see I've got 10 minutes, so I'll be really quick. Large systems exhibit one of two kinds of behaviours. Some are complicated, and complicated systems are systems that have a certain ornateness, which is understandable if you think about it long enough. Complicated is just complicated. But another kind of system is complex, and there's a big distinction, because what characterises complexity is actually the issue of emergent behaviour. Emergent behaviour means shit happens that I never expected. And this is one of these classic kinds of talks where the DNS is undoubtedly complex. And this whole root thing, the KSK role this morning, is actually all about grappling with complexity. Stuff happened, we have no idea why, and actually enough, no idea what's going on underneath it. So we were starting along in this work in something that is actually really simple. One of the best ways to deflect random name attacks that occur through recursives is to actually use aggressive NSEC caching inside the recursives, RFC 8198. It's brilliant. What actually happens is the recursive becomes your friend. As the random name attack proceeds, the signed zone that's being attacked, and it needs to be a signed zone, will actually push out range records back to the recursive. The recursive will absorb the attack. The authoritative servers are off the hook. We all go for a beer. Life is fine. But to test how far this has been used, we actually needed to use this ad system that we run to actually measure to what extent NSEC caching was being used. And for this, we got folk to query a non-existent domain in a signed zone, which gives an NSEC response. So that's what we were looking for. We did this 60 million times because ads are brilliant. We generated 142 million DNS queries. Hang on. That's bizarre. These are really simple things. Here's a name that's never been seen before. It goes through all the caches. We did this 60 million times, yet the one authoritative name server, there's only one, received 142 million queries. Why? I'm like, this is your software, guys. You're professionals. You do this for a living. You are overachieving, you bastards. Naively, no means no. One question, one answer, go away. It's not, oh, if you ask me again, the NX domain will change. It's always NX domain, no means no. Except, there's always this tension in systems that become complex, where various components have various motivations. And for the DNS perspective, the guys who write browsers are a bunch of dickheads. I'm like, they really are out of control loonies. Because the one thing they kind of expect is that everything else is free, it's infinitely available, and abusing the DNS is just one of those things you do. So the way we make the happy eyeballs experience work for users is to, of course, double the number of DNS queries that happens on startup. Because you ask for a quad A, and you don't wait for an answer. You ask for an A record as well, separately. And that's what we see. So 23% of the time, which roughly corresponds to the amount of IPv6 penetration out there in the world today, we actually see clients who put the A and quad A back to back. They're back to back so the NX domain doesn't stop it, right? 3% of folk ask for only the quad A. Now I suspect they're living in faraway places like Greenland, and in actual fact the NX domain came back before they got the A record out, or something. As usual in the internet, weird things happen sometimes. And of course, 74% only asked for V4 because the internet runs on V4. V6 is just, you know, something you do at night to amuse yourself. So we can factor this in. And if we separate out the A's and quad A's, it looks a little bit better. In actual fact, it wasn't 60 million experiments, it was 73 million because we separate out the A and quad A. They're separate experiments. We still saw those 142 million queries, but now it's a little better. We're all feeling good. It's under 2 queries per name. The DNS is saved. That's ridiculous. This is still wrong. So half of the users did do 1 query, 1 response. They might have done 2, A quad A, and they got 2 responses, so half the folk were doing just fine. But the other half, no, there was more than 2 queries. There was 2.84 queries, close to 3. Whatever you're doing for your KPAs, you're doing really good for your bonus this year. This is bizarre. So what's going on? Is this just requeries or a small number of folk being frenzied maniacs like we saw in some of that TA stuff? A small number of folk were asking like crazy. So here's the requery distribution, the number of queries for the same name, and yes, it goes up to about 1,500. There's a data point way out there that kind of goes madness, but most of them are around 1, 2 or 3 requeries. Why? I'm like, one answer is UDP sucks. But does it suck half the time? I'm like, does normal short UDP messages don't make it? It's only 603 bytes. If UDP didn't work like that, let's all go home. The internet's completely broken. So this is something else. Here's the time intervals between requeries. See those spikes? Who's responsible for 370 millisecond timers in requery? Oh, come on, OpenDNS, put your hand up. Who's responsible for 1 second? Thank you. Who's responsible for 800 milliseconds? Bind. You're not putting your hand up, but we know it's you. So part of this is you guys are requerying, but this is bizarre. Half of all the requeries occur in the first 250 milliseconds, so it's not just requery intervals and shocking network, it's something else. I said it was signed. Am I generating this because it's signed? Well, what about unsigned? Signed, requery rate 3.19, unsigned 2.51. DNSSEC adds delay, delay gives some requery, but behind this, no, even if it's unsigned, you guys don't seem to like no for an answer. You just want to ask again. So 12% of the case is DNSSEC, but the rest, no, what else? It says much the same thing. So now I'm looking even deeper about requeries per address. And what I find, it's in a log scale, is that some resolvers do requery very, very quickly, but others exhibit absolutely bizarre behaviour. I've done an obfuscation, but only in the second octet rather than the last. These folk are in enterprise networks around this part of the world, and you notice that the same query comes from the same components of 2 different subnets back to back like a machine gun. Why are you running a farm when every single member of the farm asks the same bloody query? I'm like, don't you understand what farms were about? Or you just have 20 machines all asking the same question all of the time because you know you can. There's a lot of this crap. 70% of the requeries come from resolvers that share the same subnet. Now I know all the big folk do the same technique, but I don't see intensive requerying from Google or Cloudflare. Whatever they're doing in the way they farm out their individual queries to farm members, it only seems to come out once or maybe twice. But everyone else is doing an absolutely shocking job. The other thing is it no? Well, what if I send you back yes? Wow. 41% of no generated requeries, 18% of yeses generated requeries. So if the answer is yes, most of you believe it. But the ones that don't ask 3 times, they ask 6 times. I'm like, you guys are nuts. You wake up in the morning and go, think, I'll bugger up the DNS again today. I'm going to play with A records because, you know, it's a Tuesday or something. So no matter which way you cut it, there's some awfully odd non-deterministic behaviour that a single query changes between no and an answer, and it shouldn't. There's no difference in the query mechanism. There might be a difference in the TTL, but basically in terms of question, answer, cache, same behaviour. You would have thought, but I'm wrong. Because you guys write code for a living, and when you've got nothing else to do, you just write more code and it behaves weirdly. So this is amazing. This is one of these moments where a DNS-sec-signed NX domain generates way more queries than a DNS-sec-signed real answer. Remember, 70% of the queries to the root are NX domain. Just remember that when you look at this thing that goes, the worst possible thing you can do to the DNS is to answer no, because it just encourages you to ask more, bizarrely. So I can sort of put this all back together inside the remaining 1 minute. 42% of the queries are the first query. There's a bunch of queries that come from happy eyeballs. There's a bunch of queries that I managed to prompt because I DNS-sec signed it. There's a bunch of queries that I sort of provoked because it's NX domain, and you guys hate no. Resolver farms are responsible for even more. And for the last 4%, reasons. No idea. Thank you. No questions, right? Oh, damn. We're 1 minute over. Be quick.
Dave Dagon, Georgia Tech. Very interesting observation. Does your analysis allow you to say anything about the number of independent caches that are present? Were you able to come up with a number saying this organization has X, this one has Y, based on the number of requeries or inter-arrival?
What we understand is the queries from recursives to authoritative. And we also understand the seeding event that happened in the ad. What we can't see is end client browser into the DNS. So I have no idea how the query was farmed through the first stage, I just know the answers. So in some ways, yes, we can do a whole lot more than's done here, but a lot of information very quickly. There is a lot more data that one could get. I'm not sure I'm willing to go there at this particular point in time. It starts to get a bit too interesting.
Thanks.
If I understood correctly, you have no idea whether aggressive caching works or not, right? Because it's just a mess and there is nothing to infer about aggressive caching. Is that right?
This is truly weird insofar as we've got a whole bunch of resolvers with timers and with requery answers. We've got load distributors and query farming. We've got cache refresh. What I did try very, very hard was to only look at the first 5 seconds. First 5 seconds and ignore the rest. So all this is happening straight away, which gets rid of all the loggers, replayers, all the rest of the muck, the digital stalkers. That's a different problem. So this is just straight up what happens quickly. I really find this hard to understand, so I'm not sure anyone else has a better idea. But there's a mix of code and behaviors out there in the DNS that breeds complexity.
Yeah. Maybe the situation will improve over time eventually if F5 decides to fix their DNS signers, because that's the reason why we and some other folks disable aggressive caching from time to time, because F5 just breaks half of the internet. So if they fix it, you might be able to observe aggressive caching more in Wildbot.
There is another view, because I'm a grumpy old bastard who's basically depressed at this point. 60–70% of the queries at this point have no user behind it. They're just superfluous. It's just the DNS chattering to itself. I confidently expect that percent to rise over time.
Unfortunately, yeah, that's likely.
Yeah. Yeah, thank you.
Thank you very much, Geoff. We would like to invite to the stage Maarten Wullink from SIDN Labs, who will be discussing incentivizing the adoption of new standards.
So, hello everyone. I work for SIDN, which is the registry for the .nl ccTLD, which is a medium-sized TLD with some 5.8 million domain names. And in this talk, I would like to discuss our experiences with trying to promote the adoption or deployment of internet standards. Oh, let's get. So, what is the problem? According to a recent study, the slow or reasonably slow deployment of V6, IPv6 in the Netherlands is not very good for the competitiveness of our country. We have to compete with other countries for investment in technology and innovation. And unfortunately, a lot of other countries have better or far better V6 deployment. For instance, according to Google and APNIC, the deployment for V6 in the Netherlands is somewhere between 13 and 16%, while Belgium, which is to the south of the Netherlands, is basically really our neighbor, has deployment somewhere between 54 and 56%, which is a huge difference. So our goal was to come up with a scheme to promote the deployment of V6 in the Netherlands, and also next to V6 also help deploy other standards that help to increase the security online. We did this before as well with the DNS-SEC. This turned out to be very successful. At the moment, the .nl zone has the largest number of DNS-SEC signed domain names. So we came up with a scheme for our registrars that contains financial incentives. For each domain name that's registered under the .nl zone and uses particular internet standards such as IPv6, a registrar can get a discount. For instance, for IPv6, if the domain name is reachable through IPv6, they can get a 20% discount, and for DMARC, you get a 16% discount, and for StartTLS, 4%. So in total, if you have both the V6 and the secure email standards, you can get a 40% discount on a domain name that costs roughly €3.40, which is almost 12%. And there are some other incentives as well. So if you combine all the other incentives that we have, then you can get almost 18% discount as a registrar for each domain name. This is on a yearly basis. So how does the V6 incentive look like? So we measure three things. We have measurements for the DNS, for email SMTP, and for the web HTTP. So we check for DNS, for instance, at least one authoritative name server needs to be reachable within 7 seconds. And the same for email, at least one email SMTP server through one IP address must be reachable within 7 seconds. And for the web, the same thing. We chose the 7 seconds. It's not really an arbitrary number, but it's more like a user experience number. If something takes more than 7 seconds, most users then think, okay, this service is not available. So that's why we chose it. And next to the IPv6 incentives, we also created incentives for secure email. These include support for StartTLS, DMARC, and for DMARC you would also need to implement DKIM and SPF, of course. And the way this works is that for StartTLS, we need to be able to connect to at least one mail server IP address through V6. And for email, unfortunately, we need to have much higher TTLs, much higher like timeout settings because of spam bot defenses. And it can take quite some time before you're able to complete a SMTP session with the StartTLS command. And also for DMARC, we check for the DMARC record in the DNS, and it needs to have a valid syntax, so you cannot just put any garbage in there. It has to be a sane record, and must also, like the combination of DMARC, DKIM, and SPF must make sense, and must satisfy our requirements that we have for the RSC, which RSC is like the shortcut for our registrar incentive program. And in the case of DKIM, we also had to add some additional checks, because sometimes when you check for like something beneath the domain key label, then some DNS providers will not always tell the truth. So we need to have some additional checks there. And last one, the SPF test is, we just check for the SPF record, and according to the ITF standard, the check for SPF should not contain more than 10 DNS queries. So we check all the SPF records for if they're valid, and if they contain more than 10 DNS lookups to check that, then we say they're not valid, and it's only 1% of all SPF records that fail this test. I have to hurry up a little bit. So we developed a crawler for this and can check all these protocols, scan the entire zone once every month, do this on a very limited virtual machine, and retry domains that fail. We only crawl a few web pages for each domain because we don't want to have a high impact on domain names. This is where things get more interesting. So this is the overview of the IPv6 deployment in the .nl zone. As you can see, we start almost 2 years ago with some 12% of the .nl domain zone that uses v6. And last month we were at almost, or a little over 30%. So we can see that at least at the beginning of the program, we see a very dramatic increase. And the same applies to DKIM. It's also a very big increase from almost 6% to almost 30%. DMARC, we can see the same picture almost. And StarTLS, I don't know what the funny drop is at the beginning, but the rest looks good. And yeah, finally, so the program is pretty successful. Almost 80% of the domain names registered under the .nl zone are included in the program. And we do feel that these incentives help to increase adoption of these standards. And, well, we did include StarTLS already in our program, but without Dane, it is still not very, you can still intercept email without Dane if you just use StarTLS by itself. So in the next coming months, we will also be adding Dane to the program. So we will check the TLSA records and use the hashes to validate the certificates used in the web and the email servers. So very fast. So if there are any questions,
Warren, Kamari, I'll ask this quickly. So I think it's really great that you're doing this. But the bit that I'm not quite sure is, why is SIDN doing this? Is this SIDN as an organization thought that it was worth the giving away sort of incentives? Or is the Dutch government chipping in? Or sort of who runs the incentive part?
So SIDN is a not-for-profit organization. And one of our goals is to do good to the internet as a whole, not only in the Netherlands, but worldwide. And this is one of the reasons why we do this.
George from APNIC. How much work did you have to do to decide how much incentive to offer?
Good question. To be honest, I don't know. The actual figure of how much discount each domain name should get is something that was not really done by me. I'm more of the technical implementation part.
Do you think it was workshopped with an economist, or was it just pulled from the air?
No. I think it was definitely like a collaborative process with our registrars and other stakeholders.
Sebastian Castro, Internet and said, hi, Martin. Love the work. We started doing the same.
Oh, great.
Are you checking for lies? So with the presentation from Geoff and others about that you query a name server and you get something that doesn't make any sense.
Yes, for instance, with DKIM. So when you check for a domain key label, it should basically be an empty nom terminal. Yep. And when you check the selector beneath the empty nom terminal, then sometimes you get a lie. So when we check for a random label, just to see, okay, if the response is also 0, so as this exists, then we know they're just lying, and then we don't count it.
Cool.
Jim Reid, I think this is great work, and I think you should be encouraged to see other registries try to do similar things, more per to your elbow. One question I have is unintended consequences, though. Do you have a huge a workload on your customer support people trying to apply Clue to registrars who then contact you to say, hey, I failed this test because DMARC's not been set up properly, and they then expect you to give a tutorial on how to fix those kind of things?
Yeah, so if I understand you correctly, so do we get questions from registrars that think they should be entitled to an incentive discount but do not get it because of some problem, or?
No, it's the fact that they then ask you, how do I configure DMARC to get the discount?
Exactly.
Yeah, and expect you to provide tutorials potentially for free.
Yes, that's exactly what we do. We organize like workshops for registrars, or even help them, give them like funds to hire consultants to help them with their configuration. So there's a lot of stuff we do to help our registrars to come up with correct configuration.
Great, thank you.
Okay, well, thank you.
Thank you very much, Maarten. We would like to invite to the stage Kazunori Fujiwara from JPRS, who will be presenting measures against cache poisoning attacks using IP fragmentation in DNS.
Hello, I'm Kazunori Fujiwara from JPRS. Today I will talk about measures against DNS cache poisoning attacks using IP fragmentation. The concept was first presented in 2013 by Amir Herzberg and Haya Shumon as fragmentation considered poisonous. IEEE Conference on Communication and Network Security, October 2013, and by Thomas Harabasek as IP fragmentation attacks on DNS at LIPE 67 meeting. And he presented triggering fragmentation using PassMT discovery. And a new paper was published in last year by Marx Brandit et al. As Domain Validation Plus Plus for MTIM Resilient PKI at ACM SIGSAC Conference on Computer and Communication Security. Authors poisoned CA's full service resolvers and successfully issued some certificates. And by Kenya Ota and T. Suzuki as DNS 第一フラグメント便乗攻撃の推検証と対策の検討、Reproduction of Fragmentation Attacks and Measures in Japan. And key idea of the attacks are that off-pass attackers can set PassMT value from authoritative servers to victim full service resolvers, and that the second fragment doesn't contain UDP header port number and DNS header DNS ID field. UDP header and DNS header exist in first fragment. Authentic response from arbitrary fragment size can be fetched from authoritative servers. Forged response, forged second fragment is easy to generate. If checksum of the forged second fragment and the original second fragment are the same, they cannot be distinguished by UDP checksum. However, attacker cannot know fragment ID in IP header or IP version 6 header. Next, I will show details of attacks to PassMT discovery. Attack to PassMT discovery presented by IP fragmentation attack on DNS and domain validation plus plus for MTM resilient PKI. Some implementations accept ICMP fragmentation needed and DF set with small MT value, smaller than 576, and record specified value as PassMT value. PassMT value can be decreased to 552 on Linux 3.13 or later or older, and the paper showed that PassMT value may be decreased to 296. Then I did an evaluation. This page shows evaluation method of the attack to PassMT discovery. First, generate crafted ICMP packet. Details in next slide. Second, send the packet to the host server machine by BPF or raw socket or another method. Verify the result on the host server machine. On Linux, IP root get IP address command, and on FreeBSD, this control shows passMT value. This page shows how to generate crafted ICMP version 4 packets. Crafted IP version 4 packets contain IP version 4 header, ICMP header with ICMP unreachable fragmentation needed, and checksum MTU value, and inner IP header, inner UDP header, whose source port is 53. And this page shows how to generate crafted ICMP version 6 packets. Crafted ICMP version 6 packets contains ICMP version 6 header, ICMP version IP version 6 header, ICMP version 6 header that have packet to big and passMTU value. And inner IP version 6 header, inner UDP header, and field 0 to the end of packet. And this page shows verification of the result. On Linux 2.6.32, IP root get command shows passMTU for IP version 6 destination changes to MTU 1280, and passMTU for IP version 4 destination changes to MTU 552. And on FreeBSD 12.0, ICMP passMTU for IP version 6 destination is changed to 1272. It may be 1280. And this table shows evaluation result of ICMP attack. Domain validation plus for MTIM resilient PKI paper shows that some implementations accept crafted ICMP version 4 fragmentation needed and DF set for UDP, and MTU value may be decreased to 552 or 296. And from my experiment, Linux 2.6.32 accepts crafted ICMP version 4 fragmentation needed and DF set for UDP, and passMTU value decreased to 552. And Linux 4.18.20 and FreeBSD 12.10 ignore crafted ICMP version 4 fragmentation needed and DF set for UDP. And Linux 2.6, Linux 4, FreeBSD 12 accept crafted ICMP version 6 packet to big for UDP, and passMTU changes to 1280. And NetBSD is similar to FreeBSD by source code check. This page shows summary of passMTU attack. On Linux systems, all the Linux systems accept crafted ICMP version 4 fragmentation needed and DF set for UDP, and passMTU is decreased to 552 or 296. BSD systems and newer Linux systems ignore ICMP version 4 fragmentation needed and DF set for UDP. And BSD and Linux systems accept ICMP version 4 fragmentation needed and DF set for TCP, and change passMTU for matched TCP session. And many BSD and Linux systems accept crafted ICMP version 6 packet to big, and passMTU decreased to 1280. Easy to set remotely. And then details of DNS cache poisoning attacks using IP fragmentation. This page shows methodology of the attack. First, choose victim full service Zulba and domain name and authoritative servers. Second, gets the correct response from authoritative servers. Third, number 3, send crafted ICMP packets to authoritative servers. Set auth servers pass empty for victim full service resolver. Number 4, send trigger query, target domain name and type to victim full service resolver. Then full service resolver send iterate query to auth servers. Number 5, generate crafted second fragment. Number 6, send the crafted second fragment to victim full service resolver with assumed fragment ID or all possible IDs, at most 65,536 on IP version 4. This page shows how to generate crafted second fragment. Generate crafted second fragment that have the same partial checksum value. Keep number of errors, UDP length, partial checksum of second fragment. Checksum is calculated by partial sum of the first fragment plus partial sum of second fragment. This page shows probability of spoofing, described in section 7.2 of RSC 5452. Probability of spoofing is D, number of identical out-of-state queries times F, number of fake packets divided by N, number of auth servers, number of ports, P, number of DNS ID I. And PS is changed by fragment attacks. I equal 1 because ID is in first fragment, P equal 1 because port is in first fragment. And however, divided by number of fragment ID 64-bit in IP version 4 or 32-bit on IP version 6. On IP version 4, probability of spoofing is 64,000 times larger than traditional cache poisoning. On IP version 6, probability is not changed. So fragmentation attack is effective only for IP version 4 if IP version 6 fragmentation ID is random. Next, proposal of measures to cache poisoning attacks using IP fragmentation. This page shows measures described in previous papers. Fragmentation consider poisonous proposal to limit ETNS request size payload size smaller than pass MTU 1500 and reduce maximum number of fragment cache. However, successor paper domain validation plus denied because MTU is decreased to 552. And domain validation plus for MTIM regional PKI proposed to send multiple queries and choose majority. It is one idea, however, too complex. Query by TCP is easier. IP fragmentation attack on DNS proposed to use DNS-SEC and use small EDNS requesters payload size 1220. However, domain validation plus denied because MTU is decreased to 552. And T. Suzuki proposed to use EDNS size 512. The proposal decreases DNS-SEC performance, and some authoritative servers ignore EDNS limit and send fragmented responses. And then I'd like to propose to avoid IP fragmentation. To avoid cache poison attacks using IP fragmentation by full service resolvers set EDNS requesters UDP payload size to 1220 minimal size defined by DNS-SEC RFC 4035. And full service resolvers drop fragmented UDP responses related to DNS. Then, under attacks, name resolution fails. And there is one exception. If authoritative servers are located under small MTU network smaller than 1280, set EDNS requesters responders maximum payload size fit to the MTU value or name resolution sometimes fails. And on Linux or FreeBSD, drop UDP fragment before reassembly in stateful inspection is possible. And performance considerations. Under normal condition, easiness requesters payload size is decreased to 1220. Then some of queries may be truncated and need to retry by TCP. Otherwise, no performance problem. Under pass-empty attacks, responses are fragmented and name resolution fails. And there are another proposal. Use TCP between full service servers and authoritative servers, because many cache poisoning attacks are based on UDP. However, there may be performance issue. Or DNS over TLS HTTPS between full service servers and authoritative servers will solve the issue in the future. And there are another measures. Authoritative servers set EGN0 responders payload size 1220 and set don't flag options, or use DNSSEC, or use DNS cookies, or TSIG with known keys. However, these measures require all authoritative servers support. Then I made a survey, current fragmentation status. This page shows details of fragmentation survey. Send DNS queries to Alexa. I sent DNS queries to Alexa top 1 million names, name itself and prepend www. Q-type A and quad A using unbound 1.8.3 with EGNS buffer size, max UDP size, 4096 or 1220. Query source is version 4 only with DNSSEC validation enabled, and capture packets between full service servers and authoritative servers. And unbound EGNS size 4096 case received 64,000 fragmented responses. 16 million total, and 2,438 IP version 4 addresses send fragmented responses. And assumed MTU size are shown in next slide. And unbound EDN size 1220 case, I received 26 fragmented responses. Why? Details are following slides. Assumed pass empty sizes. 2,438 IP versions for addresses send fragmented responses. And I made an assumption. Maximum packet size from each address is pass empty size. Then 97.5% addresses send 1,500 octet packets, and 50 addresses send packets between 1,276 to 1,499 octet length packets. And there are 9 addresses that send under 1,276. However, one address is strange, no query to the address, and fragmented response only, and that is strange. And other addresses send over 1,280 packets when TCP. Then all Alexa top 1 million domain names have name resolution with MTU larger than or equal to 1,280 or small responses, or no responses, not checked. And there are strange behavior. I found strange behavior. Some DNS servers ignore EGNS payload size. 11 addresses ignore EGNS requesters UDP payload size 1,220 and send 1,500 octet packets with fragments. Please try These two examples, they send large responses. They ignore buffer size 1220 and ignore large responses. These addresses may have problems with my proposal, ETN cell size 1220 and drop fragmentation because they ignore ETN cell size and generate fragments. This page shows summary of fragmented survey. From quick test, I cannot find IP version for addresses whose pass MTU is smaller than 1280, and there are a small number of authoritative servers that ignore ETN's requested payload size. And IP version 6 nodes must support MTU size larger than MTU size 1280 and no impulse fragmentation. My proposal works well on IP version 6. Summary. PassMT discovery is vulnerable and fragmentation may cause protocol weakness. IP fragmentation and PassMT discovery are well-used standards protocol and should not be prohibited. And DNS cache poisoning attacks using IP version for fragmentation is real if authoritative servers runs on old Linux systems. However, avoiding IP fragmentation at full service servers is possible and countermeasure against the attack. And I would like to propose avoid fragmentation in DNS. It is said that DNS is the biggest user of IP fragmentation. However, it is possible to avoid IP fragmentation as much as possible. Truncation and TCP works well on DNS. It's time to consider to avoid IP fragmentation in DNS. And I'd like to write new BCP document. If you're interested, please support. That's all. Thank you.
Warren Kamari, Google. So it sounds that doing this, turning this on, will make a small number of domains unresolvable. But it seems like a small number. Yesterday when there was some discussion on the DNS flag day, I was like, I don't know if that seems like a good idea because we don't know what we would possibly do. This does actually seem like something that might be a reasonable thing to do as a flag day type thing. So, you know, everybody suffers the same sort of discomfort, even if it is small.
Yes, I think we need detailed analysis.
So, Hazel Smith, thank you for doing this research. I just wanted to ask, on the side of the countermeasures piece for fragmentation attacks, I know that the attacks that you talked about were only found to be effective against v4 hosts running old Linux kernels or other operating systems, or IPv6 in the face of non-random fragment IDs. What sort of prevalence were you seeing of those?
Pardon?
What sort of prevalence were you seeing of hosts that were running kernels old enough to be vulnerable to v4 fragmentation attacks? As in, is your proposal to turn off IP fragmentation because of the security risks, or simply just because it's just junk and we should turn it off anyway? Sure.
Petr Špaček, CZNIC. From what we see, these old kernels are very, very, very baked into all the routers you get. I mean, the router for $5 or $10, that's the kind of crap which contains the kernel 2.6 because nobody bothered to port the drivers to anything new. So it's out there, but you just don't get to see it because it's not like the machine you log in. It's the network infrastructure which sucks.
Hi there, Brian Summers from Cisco. So I've been looking into this quite a bit recently because we're pushing to support DNS-SEC, and one of the things that DNS-SEC requires is large packets. I think the problem's worse than you estimate. It seems that originally the way we calculated IP fragment IDs was random. So you'd basically want to fragment a packet, so you'd pick a random number, and for IPv4 that's 16 bits. And you'd send all your fragments with that number and they get reassembled at the other end. And then IPv6 came along and it became 32 bits, and people that write kernel code decided, we can do better than that. I think they ended up doing worse. So what they ended up doing was hashing the target IP address into a 10-bit number, and then using that 10-bit number as the hash element to use for IP IDs in a sequential manner. So if you can, as an attacker, identify which hash bucket the relationship between the authority and the resolver is, you can very easily and really, really easily guess what that IP ID is. So you don't have to spam the resolver with a whole bunch of second fragments. You can spam it with 10, and you can get away with it. So yeah, I think the problem is way worse than most people think.
Thank you.
All right, thank you very much, Kazunori.
Thank you.
I'd like to invite to the stage Shumon from the DNS-OARC Program Committee to give a quick update on the lightning talks.
Okay, so I'm just going to announce the speakers for the lightning talk. So we have 5 lined up. The first one is Identify Technology Health Indicators, Paul Hoffman. Then we have yet another talk on DOE. Oh, another DOE from Jaromir Talier. DNS Crypt from Brian Hardviksen. DNS Flag Day, Kiwi flavor from Sebastian Castro. And somewhat unusually, since we had fewer submissions for lightning talks this time than the number of slots, which I was surprised by, a member of the program committee had to step up and submit the last talk, and that was me. So you'll be hearing about Dane. So those are the lightning talks start at 4 o'clock. We'll probably ask the lightning talk speakers to gather 5 minutes before 4 up here in the interest of time. Thank you.
And Matt, for an update on the PGP signing.
Thanks. Just for those of you who are participating in the PGP key signing, just a couple of next steps for you. So sometime between now and when it starts, please go to the agenda on the Indico site, which is indico.dnsoarc.net, and download the key ring that I've put there in the agenda item for the key signing. It's OARC30.asc. It's an ASCII armored export of all the keys that were contributed. Then you should also, once you've downloaded that file, take a SHA-256 checksum of it, and we'll use that so you can confirm later on that the set of keys that you have are the same set of keys that I uploaded. So when we do that, we'll be here just at the front of the room at 1:30. Thanks.
All right, everyone. Lunch will be served in the Volti restaurant, same as yesterday. We'll be resuming back in this room at 2 o'clock p.m. And we would like to thank our sponsors, our host sponsor ICANN, VeriSign, APNIC, Diamond Key Security, THNIC, and .RI. And just a reminder, if you haven't filled out the surveys for yesterday and today, we would love that you would do so. Enjoy lunch.